Hi, today we're going to take a look at a Taylor series. Before we get into that though, let's talk about the difference between a Taylor polynomial and a Taylor series. Now, in the past we've done Taylor polynomials. For example, we can approximate the sine function, and you can verify this by using our little derivative technique, that this polynomial x minus x cubed over 3 factorial all the way to x to the 9th over 9 factorial approximates sine of x. This is what we call a Taylor polynomial. Now, a Taylor series goes on further. Matter of fact, it goes forever. Notice it's the same first 5 terms here, but I put this plus dot dot dot. That means this is going to go on forever, like a boring calculus lecture. This will go on for a very long time. This is what we call a Taylor series. And we're going to spend a little bit of time today. Series, can't spell series. Can you make it look like the word series? There we go. A series. Today we're going to spend some time on how we can write a Taylor series, and we're going to learn some shortcuts if we have what's called a Maclaurin series. So let's take a look here at our notes. Now we have a Taylor series right here. This is a general form for a Taylor series. Now if you notice, it's the exact same thing we did when we did the Taylor polynomial. We have our Taylor polynomial right here, but we got this plus dot dot dot, and we end off in a summation. Now I like the summation. I'm going to show you a couple of different ways you can write these as we go through these notes. Now, thing to remember, if c equals 0, we do call that a Maclaurin series. We're going to talk about that one later on in the second example. So we want to write a Taylor series for the following exponential functions centered at c equals 2. We want the first 4 non-zero terms and a general term. So I'm going to start with my derivative process. We get f of x equals e to the 5x. F prime of x, we get 5e to the 5x. The second derivative, we get 25e to the 5x. And the third derivative, now I'm going to stop at the third derivative because remember what it's asking me to do. It's asking me to go out to 4 non-zero terms. That's not saying n is 4 terms. What I'm next going to do is I'm going to find the values at c equals 2, just like we've done in the past. And I can just kind of do this in my head. This becomes e to the 10th, 5e to the 10th, 25e to the 10th, and 125e to the 10th. Ha ha ha. Sometimes I like this count on Sesame Street. Next, I'm going to write my series. Now, what my series says I can do is I can write f of x, which is my e to the 5x, as this polynomial. Now, I'm going to use my Taylor polynomial to write this. So my first one is just e to the 10. My next one, so plus, this becomes 5e to the 10, be careful, over 1 factorial x minus 2 to the first. Now this does have an n on it, just n is 0, we don't need to write it there. My next one, plus 25e to the 10th, I'm using my polynomial, and this time is 2, over 2 factorial x minus c, which is 2 in this case, squared. And then my last one, plus 125 e to the 10 over 3 factorial x minus 2 cubed. Now, this would be my Taylor polynomial. To make this a series, I'm going to keep going. So I go plus this dot dot dot. The dot 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 means it's going to keep going. Now, these are my first 4 terms. 1, 2, 3, 4. Next, what I'm going to do is I'm going to add the general term to it. So I'm going to go plus. Now, to get the general term, I'm going to go from n equals 0 to infinity. And what I want to do is I want to generate these numbers. How did I get these? Well, take a look. Each one of these has an e to the 10. So I know my general term, I'm going to have an e to the 10 on top. Look at the powers on bottom. 1, 2, 3. The next one's probably going to be 4 factorial. Now you're probably thinking, this is right, n was 0 up here, so that's 0 factorial. So the bottom, I'm going to have this n factorial. Keep looking. What else do I have? I have an x minus 2. So I can multiply this by x minus 2, also to the n. 1, 2, 3, n. And I also have a 5 here. This is 5 cubed, 5 squared, 5 to the first, and 5 to the 0. So this is 5 to the n. Now, a quick way to check if you got this right, just plug in n equals 0, see if you get the first term. Or I like to plug in n equals 1. So, well, let's do n equals 0, n equals 1. Just plug them in, each n, see if you can generate each term here. Now, we're not done because this is only like a way station. It does keep going, plus dot, dot, dot. So this is how we write a Taylor series. Now, I could rewrite it down here, make it look a little bit pretty. I'll show you how I tend to like it. This is e to the 10th plus 5 e to the 10th x minus 2 plus 25 over 2 factorial x minus 2 squared plus 125 over 3 factorial e to the 10th. Whoops, I failed my e to the 10th here. X minus 2 cubed plus dot, dot, dot. And sometimes how I like to write it is just make it equal to my summation. So I don't need this right here. See, I messed up there. See, that's just my plus general term. Sorry about that. We don't need the summation here. If we want to write the summation, we write it down here like this. N equals 0 to infinity of 5 to the n e to the 10 over n factorial x minus 2 to the n. You don't want to write the summation up here because we're not adding a sum to it. So be very careful. I did make a mistake there. Probably most of you guys already caught that before, and that's really good. Alright, so that's how we write a Taylor series. Now if you go to part 2, we're going to take a look at some special cases on what happens if we have a Maclaurin series.